okay. I'll share screen. And get a blackboard. And let's recall where we were at the end of last time. We had, I'll recall, let me remind you, we were talking about the fundamental group of a knot with respect to a base point. And I had remarked that if I had a couple of lines in the knot and I surrounded them by a path, a loop in the fundamental group like that, and these lines were arcs that I had labeled by A and B, where I have, by definition, decided to label an element of the fundamental group that just goes simply around a single arc like that, label it A. Then this is going to be B times A in pi 1. And because of that, we went through the homotopy that checked that. And then because of that, we have that if we examine the situation here, where I have an element B here, let's say, and that will continue here, B, and this is A, and out coming C, like that, then I can put a lasso, a loop around the entire bottom of this. Like that. But that's homotopic to a loop which goes around the top of it. And so from what we had worked out already, we see that this implies that A times B, in the order that I have written it here, is equal to B times C in pi 1. So that means that we have two basic relationships in pi 1 that we can write down. One for the crossing that's oriented in a positive way, with an A here, and a B here, and a C there, and another for crossing which is oriented negatively, which I like to write this way. Sorry. A, B, and C. And so here we're going to have AB is equal to BC. And here we're going to have AB inverse is equal to B inverse times C. So it's the same, it's just that now you would have an inverse for the loop that goes in the opposite direction. And so we can write this as C, the outgoing line, is equal to B inverse AB in the case of the first one, and we can write it as C is equal to BA B inverse in the case of the second one. So this relationship holds in the fundamental group, and then it is the fact that pi 1 of S3 minus the knot is given by generators for the arcs and one relation for each crossing. So that's just to review what I had said last time. And this fact, is something that I'm not going to prove, or perhaps in the interest of time, I won't, in fact, discuss unless I needed to use it. But the fact is implied by what we have already observed, and a little more geometry, and a theorem called the Van Kampen theorem, which you might enjoy learning about. You can find a good exposition of the Van Kampen theorem in the book by Massey. See book, Introduction to Algebraic Topology, by William Massey, which you can find in our Dropbox, or at least the excerpt that you need, I believe. The Van Kampen theorem tells you how to find the fundamental group of a space if it's been written as, say, the union of two spaces, and you know the fundamental group of the intersection, and you know the fundamental groups of each piece. And at another point, I may actually state the Van Kampen theorem and show you how to use it. But it is necessary to kind of divide tree space into some pieces to see that these relations are a complete set of relations. But we're going to take it that the fundamental group is generated by the arcs, by these arc generators here, and there's one relation at each crossing, and these are the relations. So then, sorry. Okay. Oh, sorry, some problem here. Let's see. Huh. There we go. Let's get that onto the desktop. Okay. So now we get to where we were last time. We were seeing how this plays out. So we could look at the Truffle knot. And we have three generators, A, B, and C. And we have the relations at crossings numbers 1, 2, and 3 as follows. For crossing number 1, we have C is equal to, let's see, we have B coming in, and A is the operating one. So we have C is equal to A inverse BA. And at crossing number 2, we have that B is equal to C inverse AC. And at crossing number 3, we have that A is equal to B inverse CB. And that means that we can say that if G is equal to the fundamental group of S3 minus the Truffle knot. I won't bother to write the base point. Then it's given by generators and relations, A, B, and C, such that the above relations. And then we can simplify this. And we can simplify this by removing one generator and one relation. We can solve for C here and put it in. And we did this before, but I'm going to do it again. So that means that B would be equal to C inverse. That's A inverse BA, inverse A, and then C, A inverse BA. And also, I'll write it over here. A is equal to B inverse times C, which is A inverse BA, times B. Let's work with this one first, because the algebra is simpler. I can rewrite this by multiplying by B and then multiplying by A, and this is equivalent to ABA equals BAB. So that we have that relation. Now what about here? Well, when I write this out, it becomes B is equal to, the inverse of this is A inverse B inverse A, then A inverse, and BA, and A inverse cancels out, and I can multiply by A and then by B, and I get BAB is equal to, and that's gone, ABA. So I get the same relation. So I solve for, I remove one of them by solving for it and removing the variable, and then I find out that the other two are the same, and so that tells me that the group is actually exactly what is generated by A and B with the relation that BAB is equal to ABA. And this is a nice presentation for the fundamental group of the complement of the Truffle, and we can make some various remarks about this. One remark that we would like to make immediately is that this group is not abelian. And therefore, the Truffle knot is knotted. So this is the view from the group. I'm going to check that the group is non-abelian, and once I know the group is non-abelian, then K must be knotted, because after all, what is the fundamental group of S3 minus the unknot? Well, that is given by one generator and no relations by our method, right? There's one generator, the loop, and no relations at all, and so this is isomorphic to the integers. So the fundamental group of an unknot is the integers, and all I have to do to prove that this isn't the integers is to check that it's non-abelian, and then I know it's not the integers. So I'm going to prove that it's non-abelian in the following way. I'm going to give you a mapping, which I'll call F. I'm going to give you a homomorphism from G to the symmetric group on 3 letters, permutations of 3 objects. And this is a very simple representation. We're going to take A to the following permutation. I'll draw it diagrammatically. Interchange 1 and 2 and leave the third one alone. And B will go to leave the first object alone and interchange 2 and 3. All right? So in general, I can represent permutations by diagrams. So let me do an example so it's quite clear to you what I'm doing. Suppose I have a permutation of 4 things, and I take 1 to 3 and 2 to 1 and 3 to 4 and 4 to 3, for example. And then I will take dots 1, 2, 3, and 4, and dots 1, 2, 3, and 4, and then 1 goes to 3, and 2 goes to 1, and 3 goes to, oh, I'm sorry, did I? No, that's right, and 3 goes to 4, and 4 goes to, I did, 4 goes to 2. I'm trying to make a permutation there. So that, okay, there's my example. 1 to 3, 2 to 1, 3 to 4, 4 to 2, and 4 goes to 2. So you see, we just draw lines for, to indicate the function. But then you get what looks like a flattened braid, and I'll come back to that later, but this makes it very easy to see visually how to compose the permutations. And of course, in the permutation group, the square of a transposition is equal to the identity, and that means that you would have, I'll extend my graphics over to here, you would have, for example, that 1, 2, followed by 2, 1 is equivalent to the identity, etc. But in any case, I'm taking them to these, and let's call this one A, capital A, and this one capital B, right? And then how do I know this is well defined? Well, I need to see that ABA is equal to BAB. Claim. And we're running out of space on this blackboard, so I'll do the claim on the next blackboard. But once we see that ABA equals BAB, that's the only relation, so then we have a well-defined homomorphism. And furthermore, I claim this is onto, that is, the permutations are generated by the two transpositions. But we know that all permutations are generated by transpositions. These are the two basic transpositions. So once we've checked that, then we know that G must be at the very least non-abelian, because if it were abelian, it would go to an abelian group, subgroup of S3, but S3 itself is non-abelian, and that's the finite check. So that's the group theory of this. Let's just verify that bit about the permutations. Okay. So I have A is equal to transpose 1 and 2 and leave 3 alone, and B is equal to leave 1 alone and transpose 2 and 3, and then I want to look at ABA. So I'm going to multiply in order this way: A, then B, and then A. And you'll notice that this is functionally correct. 1 goes to 2, and then 2 goes to 3, and so on. So I'm just composing the functions. And on the other hand, BAB, that's equal to B, A, and B. And now you can just look at the composite and see this is 1 goes to 3. This is just write it out. 1, 2, and 3. And 1 goes to 3, 2 goes to 2, and 3 goes to 1. And this one is 1 goes to 3, 2 goes to 2, and 3 goes to 1. So they're the same permutation. Topologically, you see that you could think of it as this line here is getting to move over here, and lines can move across one another because we don't care. We only care where it starts and where it ends. And so the two pictures are isotopic to one another as flat pictures in the plane. So this checks that we do indeed have a mapping from the fundamental group of the Truffle knot to the permutations on 3 letters that's onto. And indeed, that it generates is also interesting to see from the pictures. What are all the permutations? They are the identity, they are A and B, and then there is this one, and there is this one, and there is this one. Those are the 6. And this is BA, and this is AB, and this one is ABA, as you see. And that's a complete catalog for the symmetric group on 3 letters. You may be interested in what kind of presentation we are talking about for the symmetric group on n letters. So let's just take a moment and look at what that is. I'll use another slide. So if I let Ti be equal to the permutation that interchanges I and I plus 1, and here we have n strands. So if we have n strands, so that we're dealing with Sn, then I will run from 1 to n minus 1, right? Because, yeah, for example, in 3, you had T1 and T2, right? T1 and T2. And I'm labeling it by the first strand, so I don't get a T3 for S3. These are the generators of Sn. And then Sn is, in fact, equal to the group generated by T1 through Tn minus 1. And the relations are Ti squared is equal to the identity for I equals 1 to n minus 1. And Ti plus 1, Ti is equal to Ti plus 1, Ti plus 1. And also they commute when they're far apart. That's the story. That's a presentation for the symmetric group on n letters. And you could have some fun proving that for yourself if you're interested. I do point out to you why the commuting is happening. This you already saw. This is the ABA equals BAB generalized to the ith place. But what about the commuting? Well, look at this, for example. Here we have in S4, we have T1 and then T3. And on the other hand, of course, I could do T3 first and then T1. So they commute if they're sufficiently far apart. And if they're only one strand apart, they're sharing a strand, then we have this relation here. Now, one of the reasons that I brought this up is because we can compare this way of thinking about permutations with braiding. And in braiding, we have this. We have a crossing and consequent weaving patterns instead of just an interchange. And again, I need a new blackboard. So if I were to draw a braid, for example, I might draw this. Let's take that braid. If I have a braid here, this braid is in B3, the 3-strand braid group. And here that we are taking diagrams more seriously, because you see the braid is actually thought of as an entity in the knot theory, as it were, where we have 3 points at the top and we have 3 points at the bottom, and we have arcs which are embedded in 3 space, which go always downward and are unknotted and going from top to bottom, and they don't necessarily go back to the initial point. They go from, in this case, 1 to 2, and this one goes from 2 to 3, and that one goes from 3 to 1. And you have braid generators like the permutation generators, but we have twist over and twist under. So we're going to have generators sigma I, which will be a bunch of strands in an n-strand braid group, and then in the ith strand, we'll have it going like that. That's my definition for the orientation in the braid of that, and then it continues on to the end with n strands for the n-strand braid group. And we also have the inverse of that, which is exactly this with the reverse here at that point. Everything else is the same. And then we are taking braid multiplication by taking a braid. I'll just do 3 strands and another braid and plugging them into one another like this. Bottom strands of one to the top strands of the other, and then again asking that it be fixed at the top and fixed at the bottom, and you're allowed to isotope it in the middle, and this is the product of the 2 braids, just like we had product of permutations. And the braid, and then Bn is a group under this multiplication. And furthermore, Bn has the following presentation. Sigma 1 through sigma n minus 1, just like the permutation group, you see? Sigma 1 through sigma n minus 1. So in the case of 3 strands, we'll write it down in a moment. And then no relation about the power of sigma I. In fact, they don't have any relations. It turns out that sigma I has no order. It has infinite order in the braid group. But we still have the relation that we saw in the permutation group that I wrote, and I'll write it the same way. Sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I plus 1. And we also have that sigma I and sigma j will commute when the indices are greater than 1. So this looks just like the symmetric group, except that it's missing a relation that would say sigma I squared is 1. It's not 1. And this is the presentation of the braid group. Bn. So I'm not proving that, but you can read about it and use this as a starting point. The point that it means that if you were to write a braid and you wrote another braid, then the two braids are equal if and only if you can get from one to another by a series of these moves. But what are if you think of these as moves on the braid, and you can think of them as moves, and then it begins to look like Reidemeister moves, and that, in fact, thinking in terms of how we proved Reidemeister moves is one way to understand how to prove the theorem about braids by doing something analogous. I'm just creating a box in which I can illustrate something. In terms of sigma inverse, you see, that's what this looks like. This looks like sigma inverse is equal to the identity, right? Sigma I inverse equals the identity. I've drawn it only in the case n equals 2, but it's the same pattern inside the larger pattern in general. So this is a Reidemeister 2 move. And the other identity, sigma I plus 1, sigma I, equals sigma I plus 1, sigma I plus 1. Well, you see it's a Reidemeister 3 move. So this one here, this corresponds to this, saving me the trouble writing it again, right? And so you see what we're saying. It's given that inverses do each other in, but what it really means in terms of the braids is the Reidemeister 2 move. And we're saying that the two braids are equivalent if you can get from one to the other by Reidemeister 2 moves and Reidemeister 3 moves. And we don't have to worry about Reidemeister 1 moves because for braids they never happen because braid strands always go downward, they never go back upward, and so they never have a curl in them, and you never have to deal with Reidemeister 1 moves. So perhaps that makes it almost intuitive that the braid group is in fact described in this way by the algebraic analog of the Reidemeister 3 move, the algebra and another relation that has to do with strands being far apart. The braid group was first defined by Emil Artin, and you might be interested to look in the Wikipedia and find out about the history of that and what he did with it. But it's been around for a long time and very important for knot theory because it gives us a group structure on the topology itself. And there is an excellent theorem due to Alexander, which I'd better tell you about on the next slide. Before I do that, maybe I want to stay on this slide for that purpose. Do I have enough room? I just wanted to make a comment, and I think I will make that comment right here rather than go to the next slide. This comment is the following, that the braid group goes onto the symmetric group on n letters. And I'll say use the presentation below. And take sigma I to Ti. And of course, we're now done, but maybe we want to discuss it a little bit, right? Sigma I, if you take sigma I to Ti, then these relations are all happening in the symmetric group. But then furthermore, sigma I, which isn't squaring to 1, is forced to square to 1 when you go to the symmetric group. So in other words, you can say that if you take the braid group and you make every generator of the braid group square to 1, it turns into the symmetric group. And of course, on the other hand, what I'm really saying is that the braid this braid is going to go to, in this braid in B3, is going to go to an element in S3, and that element is 1 goes to 2, 2 goes to 3, and 3, pardon me, goes back to 1. I mean, aside from the fact that I can say it formally in terms of the way the presentations map to one another, I can say it just directly in terms of the concept of the braid, because you have 3 starting points, 1, 2, 3, and you have 3 ending points, 1, 2, 3. And the braid is more than a permutation, but the braid implicitly creates a permutation because you start at strand 1 and you end at strand 2, so that, and so on, and that gives you a permutation, and that permutation is associated with the braid. And what I described by saying take sigma I to ti is exactly that. So you can think of it in terms of the formalism of the presentations, or you can think of it as a direct and intrinsic property of the braids themselves, that they have associated permutations. And from the point of view of permutation diagrams, you can think of a braid as a permutation with a lot of extra structure on it that's topological. Okay, so that's saved having to erase and go on to the next slide. We'll keep that. And now go to the next slide. Now, one of the cool things about braids is Alexander's theorem. And Alexander the Alexander theorem is that every link, or not, is equivalent to, isotopic to, the closure of a braid. So what I mean by that is the following. You have a braid here, 3 strands for our illustration, and the closure of that will be obtained. There's more than one way to close a braid, but this is the standard closure, if you like. We just do this. So you could describe this to yourself in some ways. One way would be that you take the strand, and just close it up by doing this circular process. Another way would be that you take the braid and you sit next to it an identity braid, and then you close the top, because you compare these off, you got an even number of things, and you pair it off at the top like this with caps, and you pair it off on the bottom with cups, and you obtain a closed object. For example, let's do an example or two. Suppose we took the braid that we were looking at a little while ago and close it. I think the braid we were looking at was this one. It doesn't matter, but we'll take its closure anyway. This is the closure of the braid B. So I get some knot. What knot did I get? Is it a recognizable knot? 1, 2, 3, 4 crossing knot. There's only one 4 crossing knot. Must be that it's the figure 8 knot. And indeed, if I were to take this closure strand, pardon me for doing this by, oh, well, maybe it's more cricket here, since we might have this slide as an illustration later, to copy it and then play around with it. So There's our guy. I want to make it look more like a familiar knot, so I take this arc here and swing it around. Like that. And maybe you would like to contract this one a bit so that it comes in here like that. That would be prettier. Yeah. And there it is. It's your figure 8 knot. See, there's the figure 8 knot right there. And I did that because I could now kind of show you what the issue must be in thinking about Alexander's theorem, because we just checked that this is isotopic to that, right? But suppose I had been given the figure 8 knot, then according to Alexander, I could find a way to turn it into this braid or some braid that would close to the figure 8 knot. And this is not obviously a braid. It does a sort of little knot on a rope, and there's this thing going around here. But what we're looking for a braid is to have the entire thing circulating around an axial point, right? Where the axial point could be in the plane for a planar diagram of a braid, but we want it to always be circulating around in the same direction, so that if I were to put arrows on it, we would see this going all the way, always going around in the same direction. And so Alexander figured out a way to convert any knot into a braid. And I think I'm going to not tell you how Alexander did that. You might be interested in looking it up or trying to do it yourself if you were so inclined. So you might take a rope, tie a knot in it, and then see if you can convert it into a braid, in the sense of converting it into something which is circulating nicely around an axis. But I'll tell you a hint. Alexander proved it by choosing an axis and then improving the knot with respect to the axis. So you can ask me to show you how that works next time, but the idea is you would choose an axis. Like, we could try it on this diagram just for a moment. Let's say I decided that this was my axis and I'm going to start walking along the knot. And I keep walking, and I'm good for a little while. I'm still going around this axis from here, still going around this axis, but now I'm turning in the wrong direction. So at this point, I'm going to take this arc and I'm going to throw it over the axis. Whoa, what the heck? Let's do a few moves of this on the next slide here, and I'll show you how the geometry of it looks like. we have room on the next slide. There's our picture again. And another copy of it. All right. Now I said that I didn't like this arc. Let me show you the bit of arc that I'm unhappy with. Okay. So I'm going along from here, and I was pretty happy until I got to here, and then this arc is starting to go in the wrong direction. I don't like this. And I can't go much farther than this because I'm getting an undercrossing, so I'll go this far. So I'm going to take this arc, and I'm going to erase it. And I'm going to swing it around the axis. So actually, I have room to start my swinging of the arc inside there, so I will. So I'm going to swing it around the axis. And then I have to come back to where I was in a correct way. So that means I'm going to have to go over here and come back in. Yep. So now I've improved my situation with regard to that axis, huh? In fact, I've improved it enormously. I'm very lucky because, or maybe I'm not as lucky as I think. Let's see. I can keep on going, and I'm still, I'm almost lucky. At this point, I'm good, but now I'm not going around the axis. The axis is outside. So I swing this arc over the axis as well. Let's do that in one more picture so you'll have a little record of these pictures that are doing this in stages. Yeah. All right. So my next move in following Alexander's strategy, I just move that a little bit and move this a little bit. Okay, let me go back to blue and black, or maybe I'll do red. All right, but now I'm shifting that over across the axis. That was an easy shift across the axis, okay? Now I keep on going. I'm still going. Now I'm going around the axis. This was straight. Oh, I'm back where I started. It's a braid, you see? So I start here, and I do this, and then I do this, and this is now a closed braid. That's Alexander's method. So if we wanted to make a better looking closed braid out of it, let's see. I'll take that, okay. Then this, and then this, and then finally down here, this goes over, and that goes under, and I'll mark the points. Now I'm at these 3 points for the bottom of the braid, and I have these 3 points for the top of the braid, and we have to close it, of course. Well, I won't close it. I'm unclosing it. I'm unclosing it to form this structure here, and there's my braid, which I'll call beta, and beta bar is this guy here. Okay? So you see, once you get it circulating, then you can cut away or just cut it somewhere and open it up, and you end up with a braid. This isn't exactly the braid we started with. Must be related to the braid we started with, close to the same knot. But I believe the braid that we started with was this one. That was B. And we have the B bar is equivalent to the figure 8 knot. And we have the beta bar is equivalent to the figure-8 knot. But of course, we did some isotopies from beta bar to get to E. We did these isotopies, and we didn't. And we did some isotopies to get to there as well. So there were some isotopies floating around. But if you were to just close these two together, you might get a hint about what happened here. Let's see. Let me look. Yes, I see. All right. So let's compare directly the closure of B and the closure of beta. All right. So I'm going to go by closure here. And I'm going to go by closure here. Da dee da la la. Okay. Running out of space there a little bit. Just a minute. All right, now, they're not the same. This one began with a sigma 2 inverse, and this one began with a sigma 1, right? But here's the sigma 2 inverse, and here's this, and here's this, and this one is down on the bottom instead of up on the top, right? You see this? This guy is down here in this one, and he's up here in this one. That makes it a different braid. As a braid, this one is sigma 1, sigma 2 inverse, sigma 1, sigma 2 inverse, right? Let's write it. Sigma 1, sigma 2 inverse, sigma 1, sigma 2 inverse. And this braid is sigma 2 inverse, sigma 1, sigma 2 inverse, sigma 1. In one case, you have the sigma 1 on the left, and in the other case, you have it on the right. They're definitely different in the braid group. But when you close them, why, this crossing could just migrate all the way around the loop and end up at the bottom. So there's the isotopy between them. You see it very clearly. These are isotopic as knots, but not as braids. And there's an algebraic way of saying that. I can say it in the following way. I conjugate B by sigma 1. Sigma 1 inverse B sigma 1 is equal to beta. This is beta. This is B. Conjugation has the same effect as taking something off the top and putting it down on the bottom in this case, right? And furthermore, you can see that conjugation of a braid by any other braid will leave the closure alone. I'll say that on another slide so that it's clear to what it is that I'm saying. But you now have a picture of Alexander's theorem. What I've illustrated here really does always work, and you can think about that after you give it a try. You choose an axis. You have your knot, you want to convert it into a braid. You choose an axis, you start walking along the knot, and when it starts to go wrong with regard to that axis, you flip it either over or under the diagram so that it goes around the axis. And then you keep on correcting in that way as you walk all the way around the knot. And by the time you get back to where you started, you're done. It's a miracle. So, very fundamental theorem. with a very beautiful geometric proof. And it's not the only proof either, because people have thought about this for a long time, ever since Alexander did it in the probably 1920s or 30s. I have to check the history. But in any case, people have devised other proofs, and the other proofs often have some extra information that comes along with having them. So it's worth your while, if you're interested, to try this out on some knots and links and see how the conversion works. Let me continue, as long as I got this far, with the description of the question of how can it be that we should look at this correspondence of knots and braids when it is clear that many braids could correspond to the same knot? What is the answer to that question? And I just showed you that conjugation of a braid will close to the same thing as leaving it unconjugated, and let's see the generality of that. So this is really very, I always use 3 strands for my illustrations, but everything that I say is completely general, right? Here's a braid. Now let me put another braid in here, and let me call it G. And put another one here, and now let's let that be G inverse, okay? So this is GB, G inverse. But now what happens when I take the closure of GB, G inverse? Oh, I see. I'd better not use bar for inverse, since I'm using it for closure. I'll try to be careful about that if it comes up again. So let's look at the closure. I guess you've already understood exactly what I'm saying here, but I thought I'd better say it formally out so that you have it in front of you. You see what happens here is that the G and the G inverse can slide right up into one another, and then they cancel out because they are inverses, so that this is isotopic to the closure of B. So we have that GB, G inverse is isotopic to B closure. And this is one way in which many, many braids can close to the very same object. So there's a many-to-one relationship in closure from braids to knots. And it's worse than that. Worse than that. Consider the following. Here is a braid that closes to the Truffle knot. Gamma, and gamma closure, Truffle knot. Fine. Now look at this. I take this same little braid, gamma, whose closure is the Truffle knot, and I add another strand. So now this is in the 2-strand braid group. I add another strand, so we're in the 3-strand braid group, and I put a little twist here. Okay, so I call this gamma prime. And gamma prime is equal to sigma 1 cubed sigma 2 belonging to the 3-strand braid group, right? But what about gamma prime closure? Well, right? you come around here, and all you got was a loop and a crossing. So we got a Reidemeister move to happen in which would never happen with the braids, but it happens when you make a closure because of the loopiness of the closure, and this is equivalent to gamma. And just do a Reidemeister 1 move, and it's equivalent to gamma. So you see that this is completely general. This is called the Markov move. So the Markov move, I'll draw it in general in a moment, but the Markov move is you have a braid, you embed it in the next up braid group by adding one strand on the right, and then put in a crossing over or under. And then the closure of that will be the same as the closure of the original, because the difference between the original and what you just did, in fact, just for the sake of indicating its generality without going and drawing it all over again, I just put a black box here, a red box, yeah? And then we take the red box and we add one more, whatever is inside it, and we add one more strand and a crossing, and then we find that the closure of that is going to be the same as the closure of the original. So that's another way in which you can have many different knots in different sizes of braid groups that will close, or different braids in different sizes of braid groups that will close to the same knot. But there's a wonderful theorem, the Markov theorem. And the Markov theorem is that B closure is equivalent to B prime closure if and only if B is equivalent to B prime by Markov moves. And B and B prime belong to Bn and Bm, respectively, two different braid groups. Because like this one, gamma belongs to B3, and gamma prime belongs to B3, right? And gamma belongs to B2 in this case. Well, I already said that. So I have two braids in two different braid groups, and now this is the Markov stabilization move, so-called, and this is conjugation. And the Markov moves are conjugation and stabilization. So in other words, the two examples that I've just given you of ways in which two knots, two braids could give you the same knot are the generators for the theorem that says that two braids will give you, two braid closures will be equivalent if and only if you can get from one to the other by either conjugation or Markov moves. And of course, that includes equivalences of braids along the way. So if you want to know whether two knots are equivalent, you can solve the problem in principle by representing them by braids and then trying to determine, if you can, whether the two braids are equivalent by Markov moves, whether there's some sequence of conjugations and stabilizations that will take one to the other. That can be as hard as anything else, but there are consequences to this in terms of getting invariance of knots and links, because you can look for functions on braids which are invariant under the Markov moves. And we'll get to that at a certain point. It's now heading into the last 15 minutes of our time. So I want to go back and make a comment about the Truffle knot group and then go forward and say more about knot polynomials. What did we find out about the Truffle group? Reflect on it now. We have that G is equal to the fundamental group of the complement of the Truffle knot is generated by A and B such that ABA is equal to BAB. But you know now from what we've just said that this is isomorphic to the three-strand braid group. To which I think I would remark, exclamation point. It's a nice coincidence, right? I should come back to this and prove to you that it's not a coincidence, that it actually is a fact of life that has to do with the nature of the Truffle knot. But I won't do that this time, but I'm going to say to you that it is related to the fact that, let's call this not T for trefoil, that T is equal to the variety of z squared plus w cubed intersected with the three-sphere, where I think of the three-sphere as equal to the set of two complex variables such that the sum of their squares is equal to 1. So this variety, these are complex variables. The variety of z squared plus w cubed equals 0, of course, is what I mean, is a surface in C cross C, which is isomorphic to R4, and the unit sphere in R4 is a three-sphere. So you have, in schema, you have a variety with a singular point at the origin, and you have a little sphere here near the origin, the three-sphere, and you intersect with the three-sphere, the surface, and you get the Truffle knot. The fact that this ends up being related to the three-strand braid group is related to the fact that there is an algebraic structure in back of the Truffle knot like that. And it's something that we can talk about at another point. But it is intriguing, and it shows you that you have a picture of this group. You see, hard to get a picture of this group, loops going around the Truffle knot. But by means of the translations we've made, we have that A and B can be thought of as these braids, right? Sigma 1 and sigma 2. And so if you're wondering what does a certain word look like in this group and is it equivalent to another word and so on, you can go over here and look at this. Now, all that's fine, but I want to get back to quandles, and I also want to get back to doing Jones polynomial and things like that I haven't gotten to yet. So I think I'm going to stop with quandles right now and just introduce you to the Jones polynomial formally for the next few minutes, which looks completely different. So what I'm saying is that we're going to stop this story, but we're going to come back to it because remember, we defined the fundamental group of the knot because we could see conjugation in there and because we had already checked that conjugation formed a quandle. And so we have seen implicitly, without going into the whole language of it, that there is a quandle structure related to the fundamental group of the complement of any knot. And this is one of the ways in which I can go to get you the Alexander polynomial, and we'll talk about that. But I think it's time to introduce a different aspect of things, which is that one can get some invariants that are very deep by doing practically nothing but Reidemeister moves. So let's jump to that and put it on the table so that it's something you could think about also over the week. So there's a history of skein polynomials, but I'm going to go directly to the bracket polynomial and show you how it works. So we're going to talk about the bracket state sum for a few minutes. And we don't have time to do everything here either, but I just want to get it introduced to you. So I'm going to do the following thing. I'm going to associate to a knot diagram a polynomial that I call bracket k, and bracket k is going to be a polynomial at the outset. It's going to be a polynomial in variables a, b, and d that commute. Okay, and this is going to associate a polynomial to a knot or link diagram. So we're going to have it well defined at the level of a diagram. We aren't going to use Reidemeister moves. Then we'll see what happens to it under Reidemeister moves. And the rules for doing this are as follows. If there's a crossing in the diagram, then you are going to write it as A times the diagram obtained by removing the crossing this way, plus B times the diagram obtained by removing the crossing this way. And if there's an extra loop in the diagram disjoint from the rest of the diagram, then you are going to multiply by D. And for our purposes, since we like it normalized, we're going to say that this is equal to 1. Now, the rule for choosing A and B is the following rule. Label their crossing this way. A is here and B is here. The A is on the left as you approach the overcrossing line walking toward it, okay? Either way, okay? So that tells you where the A's are. The A is on your left. The B's are on your right as you walk toward the crossing. And then the one that I've called the smoothing, that I've called the A smoothing, is obtained when you smooth it in such a way that the A's see each other. And if you smooth it in such a way that the B's see each other, you see the other. In the interest of time, I'm not going to do the state part of the state sum today. We'll get to it next time. I'm going to assert that this is well defined. This is well defined. You might worry that it would depend on the order in which you did it, but in fact it doesn't, and it'll be easy for us to see that even if we just start calculating it, we'll see why it's true, and we'll get to the state sum that way. I just want to show you how to calculate with it and how to think about it a little bit. So let's suppose, for example, that we wanted to calculate this diagram. Then that would be A times smoothing it this way, plus B times smoothing it the other way. And now I can continue to follow my rules here, and my rules are A times 1 plus B times D times the value of a loop, but we agreed that the value of a loop is 1, so this is A plus BD. And you see that by removing the crossings, smoothing them out, and continuing calculating, we go from diagrams to polynomial. Okay. Now, what's the strategy here? To understand that it's well defined, so this is a relative of graph polynomials, where you have polynomials assigned to graphs, well defined in terms of the graphical structure. But then we want to investigate what does it do under Reidemeister moves, and see whether we can get not invariant out of it by maybe specializing the variables or watching how they behave when the diagram undergoes a Reidemeister move. And we have time enough to see how that goes. So let's continue with that and watch it. Maybe one more example would be good. So I want this. According to my rules, I could choose this crossing and expand it. And then I would get A times smoothing it for that crossing. Plus B times smoothing it the other way, this way. And then, of course, I could apply what I had just learned, but let me just go and do it again quickly. So I get A times the evaluation of this, which is going to be, let's see, the A is this way, so I'm going to get AD, because I have an extra loop here. I'm going to get AD plus B. Plus B times, now the A smoothing is this way, so that's going to give me, oh no, I'm sorry, the A smoothing is this way, which is just going to give me an A, and then the other way I'll get a BD, so I'm going to get A plus BD. So I won't draw them our diagrams for that. So then we could collect terms and we would get A squared D, A squared plus B squared times the D plus AB and BA plus 2AB. You see? Polynomial. Right. And so it goes. But our problem for the last few minutes here is what happens to this under a Reidemeister move? So let's find out. Let's take the second Reidemeister move and work out what happens to this. So in this case, I'm going to draw the 4 diagrams that I would get from smoothing it, you see, because I'm going to have 4 terms. If I did this one out, I would have had this term one way, this term one way, and there would be 4 different contributions. So let's draw the 4 contributing terms. One way is the A smoothing this way, A smoothing that way. So A smooth this way, A smooth this way. All right. So there's an A for that, and there's an A for that. Okay. Now we have an all right plus between them. And then I could turn this one into a B. Or I could turn this one into a B. Or I could turn them both into B's. So now you see that the result of this is going to be A squared times this diagram plus AB times that diagram plus ABD times this diagram and B squared. Now let's see here. These are all like horizontal line smoothings, and that's a vertical line smoothing, so I can separate them out. And I'm going to get AB times the vertical line smoothing plus And then the horizontal line smoothings, I'm going to get an A squared and a B squared and an ABD times a horizontal line smoothing. So that's how it behaves under a second Reidemeister move. This is the kind of behavior I would like it to have if it was going to be invariant, but there's an extra term here which it picks up. So if you're a very committed algebraist, you might want to just keep it this way and keep separating out the algebra that are the error terms and understand where the core algebra is that relates to undergoing Reidemeister moves. But if you're willing to cheapen the algebra that's already there, we could make it exactly invariant, and that's what I'm going to do. I'm going to take B equal to A inverse, and I'm going to take, and that makes AB equal to 1, and then I would have A squared plus A to the minus 2 plus D, because AB is equal to 1, equals 0. So I'll take these two equations to be given. D is given to be minus A squared minus A to the minus 2, and B is given to be A inverse, and then using this bracket of this is equal to a bracket of this, and it's invariant under the second Reidemeister move, and we're on the road to getting something that we can calculate from a diagram that's invariant under isotopy of knots and links. Very simple. Oh, sorry. There we go. But of course, that's only the, so far, here's our progress. We have that this is going to be equal to this with A and B equals A inverse, and D equals minus A squared minus A to the minus 2. Now, what about the third Reidemeister move? Some luck. Really, some luck. You see, according to our methods, we can expand on that crossing. And then we get A times, moving it this way, plus A inverse. I'm smoothing it the other way. But we have manufactured it to be invariant under Reidemeister moves. They don't have to be in any particular orientation. It's just a Reidemeister 2 move expands out, and it's invariant under it. So this is equal to A times the result of putting that in the middle, right, plus the same thing here. And that's equal to A times, I'm going to slide it down one, under here, plus this diagram, A inverse times this guy. And now, by a wonderful sleight of hand that is part of the mathematics, you see that this formula that I've arrived at is, in fact, the expansion of what would have happened if the crossing had been above rather than below. And in other words, we have proved that it's invariant under the Reidemeister move, third Reidemeister move. Check. So we now know that if we make this specialization, we have a function that we can compute from a knot diagram, which is invariant under both the second and the third Reidemeister move. And what about the first Reidemeister move? Well, let's do it in a little box right here. And what does that simplify to? Just minus a cubed. Because you get minus a inverse plus a inverse. So you get minus a cubed times the removal of the curl. And if you had the opposite curl, then you'll get minus a to the minus 3. So it isn't invariant under the move, but it behaves in an extremely simple way. And as a result, we can normalize out the behavior under the first Reidemeister move by multiplying by an appropriate power of minus a cubed or minus a to the minus 3. Well, just by an appropriate power of minus a cubed. And I'll get to that next time because we're out of time. But once we do that, a little bit of normalization, we end up with something which is invariant under all three Reidemeister moves and can be used to do a lot of knot theory. So this little tool, which uses nothing more than a bit of high school algebra and the Reidemeister moves, provides another entry point into doing knot theory, which is quite different from the kind of thing that we've been doing so far, where we thought about the group structures and we thought about algebra structures and labeling with algebra and so on. Here, we're taking a different tack and saying that by adding up over certain kinds of diagrammatic states, that's really what we were doing here, and adding up the combinatorics in the right way with the right balance of algebra, we can derive expressions which are simply invariant under the Reidemeister moves. And that opens a huge question, which isn't really fully understood yet, but there's a lot of information about it. What kind of functions can you define from the combinatorics of a knot diagram that will give you topological information about it? So with that, I'll stop this talk, and we now have lots of directions in which we can go as we continue to talk about the knot theory. I haven't told you about virtual knot theory yet. We'll get there. Questions or comments?
Is it necessarily true, or have you basically demonstrated, that if two knots have the same bracket, they must be the same knot?
Oh, no, that's not true.
Okay.
There's a famous method which is a method of getting knots with the same Conway polynomial, which is called mutation. Mutation is, and there are other ways, but mutation is one thing that leaves the bracket polynomial alone. Mutation works as follows. You have a box with two lines at the top and two lines at the bottom and some tangling inside, called a tangle. Tangle could have many lines, but this is a 4-line tangle. You pick it up, pick it up, cut it out, turn it around by 180 degrees and plug it back in. And it won't change the polynomial.
The bracket polynomial.
Right. It also doesn't change the Conway polynomial or the Humphrey polynomial. It's a something that doesn't change that for which many things are invariant under that. But it can give you a very different knot.
Understood. Okay.
But the other question that's related to it is, what if you had a knot which was giving you a trivial bracket polynomial? Trivial bracket means it'd be a power of minus a cubed, right? Because I have to normalize it to get 1. So suppose the bracket polynomial, but we're talking about brackets. So suppose the bracket polynomial of your knot turns out to be some power of a cubed. Well, no one has ever found that to happen except when the knot was unknotted. So one could conjecture that the bracket polynomial can detect the unknot.